Here we go. Light. We talked about sound. We have understanding of sound as a wave and how that works. Now we're going to talk about light. And of course, the reason we're doing that is because light also can be understood as a wave. But let's go back to the very beginning. Let's just ask ourselves a simple question. So we're going to ask ourselves the question, what is light? And we're back after all our interruptions. What is light is the question we were trying to ask. And the reason we ask this question is because the answer seems obvious. You point to the things in the ceiling and you say those things. That's light. But then what is it though? Like, we have a pretty good handle on, say, a stapler. Okay, I'm holding a stapler. It's made of matter. And we know about matter, and we learned about atoms, and there's little electrons and protons, and, you know, we get it, sort of. Sometimes it's hard to picture that things that small could make up bigger things, but nonetheless, we have a pretty good idea since grade 9 about what makes up material objects like matter. Is light matter? Some are saying yes, some are saying no. Well, not really, is it? It's not matter. You can't hold it in your hand. You can't do the same things with light that you can do with staplers and erasers and gorillas. Right? So what is it then? And for the longest time, in fact, you can't even see it. We think we can see it, because that's weird. We can't see light, but it has to be light to see things, but we can't see light. Look at the light bulb in the ceiling right now, or if you're at home watching this video, look at the nearest source of light around you. It's glowing, looks kind of whitish, and the stuff in the room is visible. But can you see the light that's coming out of the light and supposedly streaming down towards, say, your desk or your chair or whatever's in the room? With light that's, I can't see it. It's not there. So we actually cannot see light. We can only see light when it hits stuff. That's weird. So anyway, for the longest time people struggled with light and they tried to study what it was. And they came up with two sort of ideas. And this is going to be sort of a fast-forward version of the story of light. But anyway, two sort of ideas. One is that they thought light was like a tiny stream of little marbles of light. Little particles, because, you know, they thought about the atom and how matter is made of particles. So maybe light is made of particles, and these particles just stream along and they do stuff. And they actually did experiments, and they were able to show that in some ways light does act like particles. If you put a mirror here and you throw a ball against the mirror, the ball will bounce like this off the mirror. And if you throw light against the mirror, well, the light bounces off the mirror just like the ball would. So it made them think that it was behaving like a particle. But other people were doing different experiments, and they said, no, our experiments show that light is acting more like a wave. Because if you take waves of light, they do things that waves do, like interference. Remember interference, how two waves can sort of merge together and become one bigger wave? The particles can't really do that. Two particles collide, they bounce off each other. They don't stick together and become some strange combination of two particles, and then after they pass through, that doesn't really happen. Marbles bounce, but waves interfere, and they found ways that light could interfere. And so for hundreds of years, experiments were done, people made discoveries, and they bounced back and forth. During times when people were discovering particle stuff, they believed, well, that light was a particle. And then later, when they were discovering wavy stuff, they believed light was a wave, but nobody could ever agree. Until eventually, we realized, after bouncing back and forth for several centuries, that light is both. Light is actually a wavy particle. Which means that sometimes it behaves as a particle, and sometimes it behaves as a wave. And we just have to accept the fact that's the way it works. It's weird. And we can't argue because we have all these experiments that actually prove or actually support that idea or that thought. So if light is a wave and a particle, how can we describe it? Well, what we want to talk about specifically is the wave side of light. So we're going to focus on wavy light because we were talking about sound waves, and so the next step was light waves. Next year, if you take grade 12 physics, we'll study the particle side of light and how it does all those kind of crazy things. So what is wavy about light? Well, first of all, there's a problem with waves and light. Waves require a medium. Something has to be waving. With sound, it was pretty easy to see that the pressure waves were going through the air. It was the air molecules that were being the sort of medium for the wave to travel through. Or it could be a piece of aluminum or some kind of matter. Sound waves travel through matter. But there's a real problem with light because, you know, it doesn't take very many brains to sort of stand on the surface of the Earth and look at a nearby star, or a star from many millions and millions of light years away. And the light from that star comes to your eye, and you can see the star. And yet, this is space. Space is full of nothing. So, how is the wave transmitting itself? It's not like there's air that can have pressure waves set up. What is bumping against itself or vibrating or wiggling that causes the phenomenon of the wave to reach your eyes? So the problem is there's no medium that's clearly evident for light. Light can go through things. It can go through water, it can go through glass, but it can also go through nothing. So a complete idea of light as a wave means we need a medium. That always works, right? So they said, well, obviously light needs a medium, so we're going to invent one. We haven't discovered it yet, but we know it's there. So we'll call the medium of light a mysterious substance called ether. And the word ether comes from, if you think about the gas ether, or the liquid ether that doctors use to put you to sleep, pour it on a rag in the movies and put it on your face and knocks people out. It's an anesthetic. Well, the reason it's called this ether is because if you pour a whole bottle of anesthetic ether on the desk, it'll evaporate so quickly that within 30 seconds it'll all be gone, disappear into the air as gas. Whereas a puddle of water can take days to evaporate, right? So since it evaporates so quickly, we use the word ether to describe anything that is ghost-like or, you know, mystical, kind of like you can't really put your finger on it. It's sort of, we use the word ethereal, ghosty, vaporish, all over the place, not really sure. So this word ether is referring to that property. Whatever this medium is, it's very ghost-like because it's hard to detect. And it's everywhere. It's all over, through space, it's inside windows, it's everywhere because light can travel through it. So once they decided that this would be the medium for light, the next step was to do some experiments to prove it exists. We have to find it. It's one thing to say it. So in other words, we need experiments to try and find it or detect it. So they tried, and they tried, and they tried. And they tried. I feel like singing I Can't Get No Satisfaction. You don't know that song, so you don't get it. Some of you do. They could not detect the ether in any way. Until along come these guys named, I think their names were Michelson and Morley, and they did this cool experiment with light waves. And they set up an apparatus that allowed them to measure light traveling in the same line as the Earth's rotation and traveling right angles to it. And they were hoping to find a difference. And in so doing, they were hoping to sort of figure out if they could detect this ether and how it worked and get some of its properties. Well, amazingly, sometimes science works the opposite way you'd expect. They did not prove the ether existed, but the results of their experiment proved, pretty much beyond a shadow of a doubt, that the ether did not exist. They actually proved the antithesis of their, they wanted to prove it existed, but they proved that ether does not exist, which really is just as good in science, right? If you're 100% right, that's great, but if you're 100% wrong, that's also cool too, because now you know that's not right. So you eliminate that possibility. Okay, that puts us right back at the start. What the hell then is the medium of this light? What is it traveling through? And then people started to think about the idea that maybe the medium for light is not really made of anything that's matter at all. Maybe there is something else that exists. And around this time, of course, we were starting to notice that there were lots of things in the universe that weren't made of matter. Right? Sure, we see rocks and dogs and trees and gorillas, and they're all made of matter. But there are things now we know that aren't. Weird things. Stuff like you hear about it in science fiction, like dark energy and dark matter which is matter, but not really. You've heard maybe antimatter. What's that? So because we started to discover that there were exotic things that existed, we began to think that maybe there's something that isn't made of matter. So right around this time, people were doing all kinds of experiments with electricity. And they were also doing experiments with magnets and magnetism. And they're all like, ooh, look at this, playing with magnets. And it was lots of fun. You know, they would rub rabbits together and shock little kids in the streets, electricity experiments, static, whatever. They had a lot of fun. And of course, they were still pondering light. And it turned out, and of course this is a very short version of a very long story, it turned out that all three of these things are actually one and the same. And so the word that was coined to describe it all was electromagnetism. They're all caused by the same thing. And so the medium then for light to travel was called the electromagnetic field. That was what the medium for light was called. Now, of course, that's like me, you know, I'm giving you a definition of something that's more complicated than the thing we started with. What the heck is an electromagnetic field? So to understand that, we have to just think about what the word field means in physics. You've heard of a force field if you watch Star Wars, right? Darth Vader, Luke Skywalker, they do things with force. Maybe you've heard of an electric field or a magnetic field. Perhaps in your geography class you talked about Earth's magnetic field on the North and South Pole or something. So we have these words. We also know there's a baseball field and a football field and a field of, I don't know, magnolias, whatever. All these words mean a region or a space or an area. A football field is a chunk of land. It's a region of land. A field in physics means a region of anything, anywhere in the universe. A region of space. So a region of space. That is affected by, affected, verb is affect, affected by, or has an effect, that's the noun, an effect on a particular property. That's the way I like to define it anyway. There are lots of definitions, but that one seems to work. So a force field is a field that is affected by forces. Darth Vader, Luke Skywalker, they raise their hands up and they can somehow cause forces to act on things, to lift them up or throw them away or whatever. And a magnetic field is a field that is affected by things that are magnetic. And magnetic things would change the field or affect the field. So an electromagnetic field, then, is a field that is affected by a very particular property. An electromagnetic field is affected by or has an effect on, same thing, electric charge. Anything that has electric charge will cause the electric field or the electromagnetic field to change and wiggle and wobble in a very wave-like way. Think about a cork bobbing on or sitting on an ocean or on a pond. It's very still, there's no waves, it's just sitting there. If you go and poke the cork and make it bob up and down, it will suddenly have an effect on water. You will see little ripples all through the water as it spreads out. So the cork is having an effect on the field around it. You see that? Likewise, if you have a cork that's just sitting there, or even if you don't even have a cork, you just have, let's take a cork that's bobbing. Let's not touch the cork, but let's go 10 feet away and let's wiggle the water, splash around in the water and make waves. When those waves get to the cork, what do? They make the cork bob up and down. So the field can have an effect on the cork, or the cork can have an effect on the field, you see? Now the property there is, I guess, the buoyancy of the cork or something. But an electrically charged particle works very much like that. If I take a particle with electric charge, and it really doesn't matter if it's plus or minus, one is the opposite of the other, but for our purposes we can visualize it the same way. If you move or wiggle a charged object around, it's like being in a pond, and it will make ripples or waves all around it. And these ripples or waves will be in the electromagnetic field that surrounds all things. So waves will come out of the wiggling particle, just like a wiggling cork makes waves in the water. And if a little charged particle is sitting by itself, not bothering anybody, and there are already waves in the electromagnetic field that somebody else made somewhere else, when those waves get to the charged particle, it will feel them and it will begin to bob up and down and wiggle on the waves. So the field has an effect on the object, or the object, if it wiggles, can affect the field. So any charged object will make ripples or waves in the electromagnetic field, which is like an ocean that's invisible all around us. Okay, what do these waves look like? That's the next part. They're actually pretty complicated. I'm going to draw one, and I'll get you to draw it too, and as you focus on it, it will hopefully get locked into your mind. So we'll draw an axis to give us, or an axis here to give us that vantage point. I'll try and draw a straighter one. Let's try one more time. Good enough. I'll use a red wave that looks like this. I'm going to draw this wave here. So if I have an electrical bobbing object, electrically charged object, this wave might represent how it's bobbing up and down, or wiggling, or moving, or vibrating. And it will create this kind of a ripply wave in the electromagnetic field. But here's the cool part. The electromagnetic field has another part of it at right angles that is always attached to it. And this is hard to visualize. There's going to be another wave at the same time, and it's going to look like this. Now that picture is hard to see, so I'm going to add some little lines. I'll make them fine lines. Let's go over here. And I'm going to add them in blue. Okay, I'm going to go back and do that again. Yeah. And I'm going to add them like this. These aren't really part of the picture, but they're just visuals to give us what we call perspective. And they're just going to be like this, sort of sideways-ish. And then I'm going to add some red lines to give us perspective on the other one, just thin ones like this. And once I do this, hopefully the whole thing will kind of pop into a 3D sort of thing in your eye, in your brain, and you will begin to see that it's a red wave going up and down along the board, and a blue wave going in and out of the board. You see it now? And so an electromagnetic wave is really two waves at once that are sort of somehow intertwined with each other and always work together. So it's like very hard to visualize, but that's what it is. One of these is called the electric part of the wave, and the other is called the magnetic part of the wave. So this is why electricity and magnetism are the same thing. You can't have one without the other. You cannot make just the red wave. If you wiggle an electric charge up and down, then it will make a ripple in the electromagnetic field that follows the red wave, but at the same time it will also make the blue ripple. Magnetism is actually the result of moving charged objects. It also is electric charge. So you will always get the red and the blue together. You will never get one or the other. And that's what an electromagnetic wave looks like. And this is what light is. The light that's traveling from the light bulb down to your paper is waves that are something like this. Okay. All that's left there is to look at maybe some of the different types of electromagnetic waves. A wave is a wave, right? There's only a few things you can change. And of course you can change is the frequency of the wave. or the wavelength. So let's see what happens if we have an electromagnetic wave, which is a ripple in an invisible sort of ocean around us called the electromagnetic field that is sensitive to charged objects. So let's draw another picture. Take about a half a page and sort of look at the screen as it is now, and half a page would look like that. And I'm going to start over here on this side and work kind of backwards. Kind of like when you read Hebrew, you work backwards from right to left. We're going to do the same thing here now. So I'm going to start on this side, and I'm going to draw a very long wavelength. Now this won't be to scale, it'll just be a figurative drawing, but it'll give us the idea. So you see how the waves are very long. Remember that a long wavelength means a low frequency, right? The crests would be hitting you very slowly. These are like big ocean rollers out in the middle of the ocean, very big waves. If we put a number on here, these could be anywhere from a meter or so up to as high as a few tens or hundreds of meters even. The lambda, or the wavelength for these waves, very long. Which means they also have a low frequency. It would take a long time. One crest would hit, and you could stand around, you could wait for a while, you could light your cigarette, you could smoke it, come back, oh, then the next wave hits. And you wait, right? Play a little game of checkers with some kid on the beach. Another wave hits. Lots of time in between. These waves are called radio waves. And we use these kinds of waves to deliver messages. Radio waves. Okay? In fact, they're being used right now. And I'll give you the fast rundown of what's happening right now with this microphone that I'm using. My vocal cords are vibrating physically. They're pushing the air in my throat, making pressure waves that are physically detected. These waves are going all out, and they're hitting this microphone in front of my face. The microphone is a membrane that's stretched, and it basically gets hit by these pressure waves. Now the pressure waves are the exact pattern of my voice, right? And they hit this, and it begins to bounce back and forth with the exact pattern of my voice. Let me show you something cool. This little device over here is magnets and a coil of wire. On the video you can't see it, but you'll have to just take my word for it. It's hooked up to this little meter, and all I have to do is spin this little wire inside here, and you see the meter go. The meter tells me that electricity is moving through the wire, but nothing's plugged in. If you wiggle this wire around magnets, you make electricity. Isn't that cool? Because electricity and magnetism are caused by the same thing, wiggling electric charge. And so that's how we make electricity. Just wiggle a wire near a magnet. It makes electricity. It's that simple. So on the back of that speaker that's being wiggled by the pressure waves in the air, or not speaker, the microphone, there's a little magnet and some wire. And it wiggles. And when you wiggle the wire around, because it's attached to the membrane that's wiggling back and forth, it wiggles inside the magnetic field, and it creates electricity. Now the electricity doesn't just flow straight through the wire, it wiggles. Just like my voice was wiggling, just like the air was wiggling, just like the membrane on the microphone was wiggling, now you're making electricity that wiggles. And it's going into an antenna in this headpiece. And when it's there, the little electrons are sitting in the antenna. You can imagine them sitting there on the beach. It's a nice day. They're not moving much. But along comes this wiggly wave of electricity. Guess what they do? Woo! Playing my song, like a cork bobbing on the water. They begin to wiggle. And if you wiggle electric particles, then that's like little corks bouncing in the water. They start to make their own waves. So they make ripples and wiggles that are now leaving here and flowing all out around me into the electromagnetic field. And some of them are going into this little antenna over here on this little guy. And the electrons in there are sitting there, and they feel the ripple. And they're like, whoa, they're playing our song. And they start to dance, moving up and down like the cork on the water. And when they move, they're moving. They're charged. They create electricity. And electricity goes into the wires. And all the time, it's got the same pattern as my voice, which started all this. It goes into the wires. It goes into this machine right here, which has got a speaker, which is a big, giant cone of cardboard, basically. And behind it is a magnet and a coil of wire. When those waves get to the magnet and the coil of wire, just like moving the coil in the magnet makes electricity, wiggling electricity can make coil move inside a magnet. The opposite. So now the moving electricity makes the coil move, which makes the speaker move, which now pushes on the air in and out, the same pattern as my voice. And it pushes now into the air, which makes pressure waves which you can hear. Pretty wild, right? But all the while, aside from the pressure waves in the air, the wireless transmission and what's happening in the wires themselves, specifically in the air between us, is the electromagnetic waves that are ripples that are happening. So we call them radio waves. We use radios and devices, CDs, walkie-talkies, and all these things to communicate. Now we're going to do one thing. Now remember, I'm drawing this as a simple transverse wave, but really it looks like this picture up here. I'm not going to draw that each time because it's crazy. But that's really what this wave looks like. We're going to change the frequency of the wave. We're going to make the wavelengths a little shorter. Like this. If you shorten up the wavelengths a bit, and you get down to around a centimeter or so of wavelength, notice it's not to scale. We call this new sort of range of wavelengths microwaves. And you've heard of microwaves. We have an oven at home, cooks things. Microwaves have just the right energy. And speaking of energy, we should mention that, let me just bring this down a bit, like this. The energy level of a wave gets bigger as the wavelength gets shorter. So the energy is increasing as we go across our picture. Remember when I was making waves with the slinky, I could make big leisurely waves without much energy, but to make the little short waves, you really got to vibrate your hand fast. So shorter wavelengths mean higher energy. So microwaves have a little more energy than radio waves. They have just the right energy to drive water molecules crazy. Water molecules in particular have a funny shape, they're kind of bent, and they like to vibrate a certain way. And just like we talked about resonance with sound, how if something is vibrating in the right frequency, it can make something else vibrate. Microwaves are a vibration that water molecules just love. And whenever a water molecule feels a microwave, it just starts dancing. It vibrates, it goes crazy, right? Because it feels the wave, which means it gets hot. When you vibrate, you get hot. So microwaves make water molecules really hot. And hot water can cook stuff by boiling. So technically, everything you cook in the microwave is boiling because you're using hot water or steam to cook it. If you've ever put a piece of pie in the microwave and turned it on for 30 seconds, nice blueberry pie, when you open it up and you reach in, you feel the crust and you say, oh, it's still cold. So you go back and you put it in and you put another 30 seconds. And you open it up and you feel the crust and you go, it's still kind of cold, what the heck? So you go back and you put in another 30 seconds and then you say, this pie's not getting very warm at all. So you pull it out anyway because you're hungry and you say, too bad, I'm just going to eat it cold. You take a big forkful of this nice pie, put it in your mouth and you burn the crap out of your tongue somehow. Have you done that? Of course you have. Because pie crust has very little moisture in it. It's dry. So the microwaves have very little effect on it. Microwaves only really affect water, whereas the blueberry filling has just lots of moisture. So you're feeling the crust, which is dry and not getting very hot, but inside the filling is, so that's why it's super hot. This is why people used to think that microwaves cook from the inside out. They don't. But the inside of things tends to be more moist than the outside. So the microwaves only make water hot, therefore the middle will get hot, you see? Anyway, that's microwaves. We also use microwaves, by the way, in our cell phones. The waves that the cell phones make are microwaves, and they travel outwards and are picked up by towers and can be bounced around off satellites and can allow you to communicate. You might wonder, your cell phone uses microwaves, and you hold that near your head all the time, and yet microwave oven cooks food. I wonder if your microwave cell phone is cooking your brain. That's another story for another day. Possibly in the next video, I think I might have explained that a little bit, so tomorrow you can hear about that story. Let's make the waves a little shorter. A little shorter still. Now we're talking so short that we would be smaller than a millimeter, maybe a micrometer, between the crests. So you can see why we can't draw this to scale, because it's just an incredibly ridiculous scale. These would be called infrared waves. infra, which means under, red. Infrared waves, well, they can cause lots of things to vibrate and get hot because they are technically heat. When you go to a campfire and you are sitting by a fire, you feel the warmth of the fire coming off there. What's actually happening is the fire, believe it or not, fire is also charged particles, right? And so the charged particles in the flame are bouncing around, creating all these waves. And the infrared ones, they happen to be the right length. When they come to you, they hit your skin. And in your skin, you have nerve endings that are highly sensitive. Remember, all your molecules are made of particles that are charged, right? Protons and electrons. Mostly the electrons on the outside. So these waves can make atoms in your body do stuff and wiggle. If you wiggle the electrons on these nerve endings, that actually produces a nerve impulse in the membrane of the cells, which goes to your brain. And when your brain gets a signal from there, it's like lighting up. Oh, we have a message from the heat department that says we're feeling something warm. So that's how your brain feels the heat of the fire. But it requires this wave to come out of the fire and wiggle the nerve ending molecules in those special nerves. But they don't wiggle much else. They don't wiggle our eye membranes, our retina. We can't see the heat. They do wiggle the things in our skin, which allows us to feel it. Question? Yeah. Why is the top of the fire wavy? Well, the question is, what's a flame? Is what you're asking me, right? So have you ever heated a piece of metal till it got so hot that it glowed? Okay, it glows red or even white. If you're a welder, you might have seen that. Anytime you heat something, eventually it will make waves. When it's making infrared hot waves, you don't see anything, but you can touch it and feel it's hot. In 1 second, we're going to see what happens when the waves get shorter with more energy, or more hot, more heat. You start to produce waves that our eyes are sensitive to and that we can see. So we produce light. Now, if you heat up a piece of metal, it will glow red. If you heat up air, it will also glow. So the chemical reaction of oxygen and the combustion of the oxygen reacting with the fire, with fuel, is producing tremendous amounts of heat, and the heat makes the air around it so hot that it glows, just like a hot piece of iron. So a flame is hot glowing air. But the reason it's flickering is because air is easily moved around, and currents, wind, are blowing and changing, so the heat is being dispersed in a weird way, and you get this sort of flickering place. Basically, a flame occurs anywhere the air is hot enough to glow. So that answers your question. And it also tells us what's next. If you shorten this wavelength a little more, you will get a wave of light that can be detected by your eye. In your eye, there are cells that are sensitive to this particular wavelength. When this wavelength hits the molecules in this cell, it stimulates them, causes them to bob up and down and get excited, and produces an impulse from our retina to our brain that says, hey, we're seeing something that's red. We don't see infrared because we don't have cells that are sensitive to that particular wavelength. We would feel the heat of it, but not see it. But a little bit shorter, and all of a sudden now it turns from heat into something we can see. And then if you go shorter still, let's see if I can find orange here. The next wave would be a little bit shorter still, and it would be allowing us to be sensitive to the color orange. Guess what's next? A little shorter still, yellow, green, shorter still, blue, shorter still, and lastly violet, even shorter. Remember, the shorter you get in wavelength, the higher the frequency, and the more energy you have. Purple light has more energy than red light. Okay? We can see these colors, and so sometimes we call this section of these groups of waves, we call this the visible light section, visible light. Now, technically, all these things are light. Radio waves are light too, but they're the wrong frequency or the wrong wavelength for our eyes to detect. But they are really the same thing. If you get smaller still, something weird happens. I'm going to draw a little dashed line right here. Smaller still produces a wave with very, very short wavelengths and a very high frequency. Its name is ultraviolet. Remember, the energy gets greater the smaller the wavelength. These wavelengths are so small, they have lots and lots of energy. So far, all these waves would hit molecules in your cell and make them vibrate, maybe make their electrons jump around a bit. No big deal. But ultraviolet has so much energy that if it hits molecules in your cells, they won't just vibrate. They'll vibrate so much that they'll break apart. Electrons will be flying all over the place. We call this ionizing energy. So from this point on, from the dashed line up, the energy is so great that these things are ionizing, which means they can blast electrons off of molecules and atoms. That's bad news for us, because if you blast electrons off of things, remember, electrons are what makes things bond together. So if you blast the electrons away, you change the chemical bonds. And you could totally distort or change the nature of a molecule by hitting it like this and breaking apart of it. So imagine on your DNA. In my this morning's class, I did a little ballet to illustrate this. So in the video you can't see it, but from the laughter that it will evoke, I'm sure you will get the idea. So here's my best ballet representation of a DNA molecule. The double helix there? There's DNA. Now, the DNA normally, if we zero in on one little piece of the DNA, we can see that what it is actually adenine. It's the molecule adenine. It's kind of a roundish molecule with a little top on it, right? And it's happy. And it sits there doing its thing in your DNA. But if ultraviolet light comes along, the ultraviolet light is so high in energy, it'll hit the adenine, and instead of making the adenine vibrate or jiggle around or create a nerve impulse, it just blasts the crap out of it. And the adenine is now broken, gone, or changed in some way. So now, when it's protein making time, and your cells are coming down the DNA, and they're reading it, trying to figure out how to make the protein, and they're reading it along CCGT, CGA, CGA, GGT, AG. Oh, we hit this spot where there's a big gap where the old adenine was blown up. And they go, gee crap, what's supposed to go there? We don't know. So they call up to the brain and they say, well, we can't make this protein because we don't know what the instructions are. And the brain is like, well, too bad, you gotta make it, man. We need this protein. It's life or death. Okay, so they go into the cupboard, eeny, meeny, miny, mo, cytosine, adenine, guanine. Let's take a guanine. Sure. And they cram that in there. And now you have a guanine in there, which is the wrong instruction. So what's happening is your cells are getting the wrong information. They're going to build the wrong protein. Or not build it at all. So your body's doing without it. Or they'll build a protein that's kind of messed up and has adverse effects. If this part of the gene happens to be one of the genes that makes proteins that regulate the growth of your cells, suddenly your cells aren't going to get the right growing instructions. They might stop growing and die, which is often what happens. Or you might get an instruction that says grow faster by mistake. And the cells then are like, whoa, grow faster. It's like mitosis central. And the cells begin to divide like crazy. And before you know it, you have this giant mass of useless cells that we call a tumor. And you have cancer because of the ultraviolet light that has hit your DNA. So that's why ultraviolet light is not necessarily a good thing. And why it's ionizing. Everything that comes after this just gets worse, because the energy gets higher. After that, if you go really short, I'm going to try to squeeze these in here. So I'm going to erase the ultraviolet word. You wrote it down, so you know what that is. I ran out of room. I don't read much Hebrew, so when I work right to left, I tend to run out of room. Here's a higher frequency wave. The wavelengths are even shorter than ultraviolet. And when we discovered this wave, we said, hey, it's some kind of wild ray. What should we call it? Let's call it the X-ray. So we called it the X-ray. It has even more energy. X-rays can do some serious damage to your tissues. In fact, they're so powerful, they just kind of fly right through anything soft. And on the way, if they happen to bump into stuff, they just kind of blast it out of the way and make a mess of things. Then they hit the hard bones and they kind of collide and stop, and the bones are dense. So we use x-rays to get pictures of bones, but there's a cost to that. They actually can damage your body, so doctors are very careful about how they give x-rays. In the old days when they invented the x-rays, what they would do is they thought, hey, this is cool, and they'd go to the shoe store, and they'd stick their foot in a shoe in an x-ray machine, and they'd look at the x-ray and say, hey, look at how good your shoe fits. You can see your bones in there, everything looks great. They didn't know it was going to cause problems. And it wasn't until people started having, I don't know, green feet with 7 toes that sort of fell off in their sleep that they realized, wait, these x-rays are bad things. They damage the tissue, right? And so we don't use x-rays in shoe stores anymore. We only very carefully use them if the risk is outweighed by the potential disease you have, right? The doctor's only going to order an x-ray if he thinks the risk of the x-ray is small compared to the risk of you dying or being seriously hurt. So those are x-rays. And I'm going to erase that word too because I got to squeeze in 2 more. So you wrote down x-ray, I hope. The next one, even shorter. Very short waves now. These ones are so short and so high energy, we don't see them very often. Unless you're the Incredible Hulk. Apparently, in the comic strips, too much of this can turn you into the Hulk. They're called gamma rays. But in reality, outside the comic books, you do not turn into an amazingly strong green monster. You die very quickly. Gamma rays are commonly produced in nuclear blasts. And we really found out the hard way what gamma rays do to human bodies from victims of nuclear bomb attacks. And they basically have so much energy that they destroy anything they come across in your body. And you become a massive walking pile of dead cells very quickly. And so within a few days, you probably just drop dead. So gamma ray exposure, not a good thing. All right? Incidentally, most of these high rays are coming, all of this stuff comes out of the sun, but these are blocked by the ozone layer. Only the ultraviolet can sneak past the ozone layer in small amounts, which is why we still have to watch, because the ultraviolet can damage our skin. And of course, when you get a tan, what happens is the ultraviolet light comes in, hits a cell, damages the cell, and now there's this damaged cell, and your body's like, holy crap, we're being assaulted by something. And the way your body defends it is to quickly produce a protein called melanin that darkens your skin. So a tan is like a giant scar. It means you've already damaged your skin. Doesn't mean that you're healthy, and look at me, I have a nice healthy brown color. It means your skin has been damaged by sun and by UV light, and your body tried desperately to protect itself by creating the tan. If you stay much longer than that, you're going to get the sunburn, which is the actual damage now getting so great that it's actually visible and you can feel it. Your body does repair this damage, by the way, but slowly. So imagine if you had 3 little workers repairing your DNA. Every so often you get a little shot of UV in there, you blow a little, thymine or something, you blow that up. The workers will go and they'll fix it. They'll figure out that it's supposed to be thymine and they'll fix it by putting a new one in. But what happens if you're out in the sun on the beach and you get bam, 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 and these 3 little workers can't keep up? Eventually there'll be damage that they can't fix because they're working 24/7 and they just can't do it. And then the damage accumulates and then you end up with the problems. So some exposure to sunlight is okay. It's reasonably healthy. And as long as it's not too long term, your body could fix any damage you did get. And you might get a little tan to help next time. But what we do, of course, is we go out in the sun for far too long without protection, and we get so much damage accumulating, we end up with skin cancers. So that's really the trick about UV. Small amounts of sunlight are healthy, but too much at once, like anything, too much of anything, is probably going to cause some irreparable damage. Okay, I'm going to erase the gamma ray word because there's one more to write in here. This one sort of applies to everything past this point. We stopped giving them names. This one is so high energy, the wavelengths are so short that I'm not going to be able to draw it that far. And it's called the cosmic ray. The only place you really get cosmic rays are in supernova explosions. Giant, massive stars 10, 15, 20 times the size of the sun, with temperatures of millions of degrees in their core, blowing up into these gigantic explosions that we can't imagine, produce these high energy ripples in the magnetic field, the electromagnetic field. And of course, these will kill you like nothing. If a supernova goes off anywhere near our solar system, we're all dead within minutes. So we don't want that to happen. Now here's the interesting thing. All of these are waves that look like this. The only difference is some have the bumps closer together than others. Some have shorter frequencies, shorter wavelengths and higher frequencies. Isn't it interesting to note that yes FM, the radio wave, yes FM, cooking your dinner and talking on your cell phone, feeling the nice warmth of a campfire, seeing all the colors that you can see, getting a sunburn, going to the doctor for an X-ray, turning into the Incredible Hulk, and supernova explosions are all caused by exactly the same thing. They're all light. They are all ripples of electromagnetic radiation, and the only difference between them is the size of the ripples, the size of the wavelength. Makes you think, wow, so many different things, all caused by the same phenomenon. You know? So this is what we call the electromagnetic spectrum. It's a description of all the different wavelengths of light and what they do and how they work. Everything up to here, below it, down below, the visible light area, the microwaves, the radio waves, they vibrate things and make things move around a little bit, like the cork on the water. But everything over here is potentially destructive and actually can be so vigorous that it can break molecules and atoms apart. And luckily, the ozone layer blocks a lot of these out from the sun. Because the sun is a giant nuclear bomb, isn't it? It's a giant nuclear explosion. So luckily, it's making this stuff, but we're protected by it. And incidentally, the ozone layer is made of oxygen, and the oxygen on the Earth, most of it comes from bacteria, blue-green algae that made it billions of years ago. So we owe our whole lives to these little germs, these little bacteria, because if we didn't make that oxygen, we wouldn't have never been able to evolve, because these radiation, this high-level radiation, would kill us. And by the way, that's what we call this stuff. We call it radiation, because it radiates, these waves radiate through space. All of this is radiation. Yes, FM is radiation. We tend to think of radiation only in terms of the bad stuff over here, but it's all radiation. Green light is radiation. It's just not the harmful kind. But they're all the same thing, and they're all the waves of light. So that is sort of the intro to light, and light being a wave, and some of the cool things that result from that. And we will stop here. Tomorrow we will look at how light interacts with matter when it actually collides with stuff. Okay.